So let's pick up where we left off. Actually, we'll just do some review first. So as a reminder, one of the main reasons we care about this random non-self-crossing curve called Schramm-Loewner evolution is because it describes the scaling limits of interfaces in critical lattice models, such as the critical Ising model, critical percolation, and uniform spanning tree. On the other hand, we want to use these random surfaces called Liouville quantum gravity to study Schramm-Loewner evolution. And the story that we told on Tuesday is that if you have a random planar map with some suitable notion of conformal embedding inside the unit disk, and you send the number of vertices of your map to infinity, in the scaling limit, you get a random geometry called Liouville quantum gravity. It comes with an area measure corresponding to counting measure on the discrete side, a boundary length measure, and some kind of notion of distance. And this continuum object is defined using the Gaussian free field. Okay, so I should have mentioned this on Tuesday, but let me give a quick high-level intuition as to why we want to use Schramm-Loewner evolution together with Liouville quantum gravity. So, in short, the reason is because you get much nicer Markovian properties when you couple with the random surface LQG. At the discrete level, the story is something like this. On the left-hand side, let's say you have a random planar map with a disk topology, such as in the previous slide, and let's say it's weighted by the partition function of the critical Ising model, say with constant plus boundary conditions. We're going to explore this random planar map. Right, so we know the boundary phases are all plus, and we just keep healing, just looking at the different phases until we find minuses. Okay, so what happens here? Once you've explored the plus boundary cluster, what does the rest of the map look like? It turns out that these unexplored regions are conditionally independent Ising decorated random planar maps with minus boundary conditions. Okay, and the only information you need to know about these things is that they have these boundary lengths given by the lengths of the holes here, right? So, so in this particular configuration, I've explored the cluster. I found 3 holes of size 4, 5, and whatever those numbers are. And then you know that you have to fill in these holes with independent Ising decorated random planar maps. And the point here is the information you need is very minimal. All you need is the length of the boundaries. You know, what are the lengths of these boundary loops here? On the other hand, if you do the critical Ising model on a Euclidean lattice, you do get some kind of Markov property, right? You explore the boundary cluster, you get these holes, which you know will have Ising configurations with minus boundary conditions, but then the information you have to carry is much higher. You care about the actual shapes of these regions. So in the first case, you just carry these positive integers, which are the loop lengths. In the second case, you have the whole shape. And so for this reason, intuitively, when you couple LQG with SLE, it somehow becomes more tractable. This is a thing that has been done in physics using the so-called KPZ relation, music project called Zermologikov, which lets you do computations of LQG and SLE together, and then deduce SLE observables that are difficult directly. Okay, we'll see how this kind of idea is used in today's lecture. Okay, so again, a word of caution. Even though I will repeatedly talk about random planar maps in these lectures, the actual arguments don't use the scaling limit of random planar maps in Liouville quantum gravity. All of these stories I tell in the discrete are all for motivation. It tells you what kind of statements you expect directly in the continuum, and then you prove these statements directly in the continuum. You never pass through the random planar maps in the sense of this kind of scaling limit result. Although we will see some random planar map input later.
Okay, can I ask a very quick question?
Yes.
Is the claim that instead of studying some correlation function on LQG, you translate this problem into some observable on SLE?
That's one thing that you can do. Yeah. You can use solvability of LQG to get solvability of SLE, and vice versa. Yeah. So we'll see we'll see an example of this today. Yeah. Are there any other questions? Yeah.
So you said you usually don't prove things in the continuum by using limit. Can you do that?
So it would be very interesting to me to get any of the kind of results that I will state using this sort of limit. Normally you need to get, for the coupling between LQG and SLE, we only know how to do this directly in the continuum, except for some very special cases. Yeah. This doesn't mean that we won't use discrete inputs, as we'll see later, but mostly you have to work directly in the continuum. Yeah. Are there any other questions? Okay. Okay, good. So to define LQG, we introduce this random distribution called the Gaussian free field. It's a random generalized function on the plane. It's not well-defined point-wise. You cannot evaluate the value of the function at a single point because it's not a function. It's a distribution. But if you regularize it in some way, like you take the average, you convolve with a smooth, with some approximation of the delta function, or you take the average of the function on a circle, then you can indeed get a function, and it would look something like this. Okay, so this is a nice object. It's Gaussian. It's variances are explicit. This is pretty easy to work with. The main observables that we care about for today's lectures are going to be these random area measures called Gaussian multiplicative chaos. It's just the exponential of the Gaussian free field with some coefficient gamma, which we take between 0 and 2. And you have to regularize the free field so that you can actually define this quantity. You have to renormalize so you get a non-trivial limit. And then you can define this random measure, as we discussed on Tuesday. So one thing I want to mention here is that if you, okay, this is a typo. This second plus C should be gone. But okay, if you perturb your field by adding a constant to it, just from looking at this expression over here, adding a constant to the field is just going to change your measure by this multiplicative factor of e to the gamma c. This is immediate from this expression. Okay, so first we're going to discuss these two perspectives on LQG. This will be part review and part new relative to Tuesday's lecture. Then we'll talk about the different kinds of solvability or exact formulas that you can get in each of these two perspectives. On the one hand, the CFT perspective brings with it this rich algebraic structure, and using BPZ equations and other tools, you're able to compute all of your correlation functions. On the other hand, when you look at the LQG from the random surface perspective, it is coupled with SLE, and then it describes scaling limits from planar maps, and that gives you a different source of integrability. You can get exact formulas coming from the discrete. And so you get these two orthogonal sorts of inputs, and when you combine them, you're able to deduce new things. And we'll see how to do that to get some kind of solvability of SLE, some exact formulas. Okay. Okay, so we spoke about this on Tuesday. So the Liouville CFT stuff, this was introduced probabilistically by Antti and David Remarkably, Vargas, and then expounded upon later together with Colin Guillermo, who was here from Monday to Wednesday. And okay, I should just get into the statements. So if you recall from Tuesday, what we call the Liouville field is a very simple object. It's just going to be a Gaussian free field H plus a real number C on the unit disk. So the real number C is going to be coming from this infinite measure on the real line, which has this exponential weighting. And you can modify or perturb this field by adding insertions. So if you have a real number alpha and a point Z on your disk, you can consider what happens if you take a Liouville field and you weight by the exponential of the free field at that point. This doesn't make literal sense, so you have to use some kind of regularization and renormalization. And that allows you to define the Liouville field with an insertion of size alpha at the point Z. Okay, so this tells you how to add one point insertion to your Liouville field on the disk. I can give a second description of this object that doesn't go through this limiting procedure. You can do it this way instead, using the Derive theorem for Gaussian processes. You're weighting by an exponential function, and that's going to shift the mean of your Gaussian process. So your one-point field has the following alternative description. You sample a free field, and this constant C from this measure. This is no longer minus Q, C has got this alpha minus Q times C. Then your Liouville field is phi is equal to H plus C minus alpha times the log. So this gives you a logarithmic singularity that blows up at rate alpha when you're close to the origin. So here we're taking Z as 0. Okay, so this is an explicit description of the Liouville field that doesn't use this limiting description.
So I think you said it already, but so these aren't probability measures, right?
Yeah, exactly. Yeah, these are infinite measures. So PD is the law of the Gaussian free field with mean 0 on the unit circle, and this is a probability measure. So we're sampling this pair from this infinite measure. Yeah. Thanks for the clarification. So, okay, are there any questions? Okay, if not, I want to work on the board for a little bit. So maybe we can switch off the slides. Could we please get the slides off for the next 10-ish minutes? Thank you. Okay, right. So the Liouville field so we just saw how to define the correlation functions, the Liouville field, and now I want to recall the definition of the correlation function. So let's say you care about the one-point correlation function for Liouville, like this. We have a bulk cosmological constant, which I'm going to set to 0, and a boundary cosmological constant. And this is going to be defined to be the Liouville field expectation where you've got an insertion of size alpha at the point 0. You're going to take the average value of this quantity. Okay, so this quantity over here, this is a Gaussian multiplicative chaos. Okay, so earlier today we talked about the Gaussian multiplicative chaos on the interior of the unit disk. You can define a boundary Gaussian multiplicative chaos measure in the same way. You take the exponential of your free field, regularize at scale epsilon with some kind of coefficient in front of it. You have to do a renormalization and you take a limit. So this quantity, which we call L, is the Gaussian multiplicative chaos on the boundary, or the quantum boundary length in different words. And so this one-point correlation function is defined to be the expected value with respect to the Liouville field of e to the minus the boundary GMC. And so as we're going to see, this explicitly just becomes a moment of the Gaussian multiplicative chaos. So in this setting, and also in the setting of the works of Antti and others, these correlation functions are simply moments of Gaussian multiplicative chaoses. Are there any questions about this definition? So the Liouville correlation function with one marked point in the disk is precisely going to be some kind of moment of the boundary GMC if your insertion alpha is bigger than q. Q is gamma over 2 plus 2 over gamma is the background charge, and is infinity or 0 or something if alpha is less than q, is degenerate in some way.
Can I ask a small question about the geometry? So when you fix the singularity with conformal transformations on a disk, what is the first non-trivial geometry you get? Because in this case, this will be just some sort of a gamma function, and that's it. You won't get more structure, or do you expect some non-trivial expression from the moment?
I'm trying to recall exactly what you get in this one-point case, like what this comes out to. I think you just get gammas, not double gammas.
Yeah, so for example...
3 points on the boundary, you would get something very non-trivial.
Or 3 points on the boundary.
Or one point and one boundary point, you also get something very non-trivial.
Because in the sphere, it's like 3 points is a hypergeometric function, approximately, right?
3 point is not, it's a DOZZ function.
It's the epsilon function.
Oh, okay.
This is just some gamma function.
Okay.
Yeah.
Is it, so this moment is infinite with alpha is less than q, but in general, this boundary length, is it clear that it's finite?
Yeah, so this, I'll speak about this in a second. Yeah, so as Ellen has suggested, we're going to look at this in 2 steps. So first look at the law of the length of the boundary of the Liouville field, and then we'll use that to deduce what the correlation function is. In doing so, we'll see that that if you just look at correlation functions with this definition, you're kind of missing out on a lot of valuable geometric information. So we're not going to do anything fancy in this computation. It's just going to be change of variables from high school, maybe. Depends which high school you went to. Okay, so let's first recall our definition of the Liouville field with an insertion. It was the Gaussian free field plus some constant minus this alpha log singularity at the origin. So since we are looking at this boundary length, we really care about the value of this thing on the unit circle. And so this last term just vanishes. This is just 0 on the unit circle. So the GMC with respect to phi on the unit circle is the same as the GMC with respect to h plus c. And as I just mentioned earlier, this constant comes out and gives you a multiplicative factor of gamma over 2 times c. So now let's compute the law of the boundary length. So we're going to compute the size of the event that your boundary length is between two real numbers. Okay, and this will just, this is like computing the CDF, the boundary length. We're just going to expand the definition. Okay, I haven't done anything fancy. So we're just taking expectation with respect to free field H and integrating over the real number C. And we're looking at the indicator function that the length is between A and B. And now we just do a change of variables. So we let y, I should write it down. So y is going to be a real number, which is e to the gamma over 2c times this GMC of the free field H. So we differentiate dy over dc. This is just exponential in c, right? So you just get this gamma over 2 factor times the whole thing. So we're just going to do that change of variables now. Okay, so what is e to the alpha minus q times c in terms of y? Well, we have to divide by the length, and then we have to put some exponent to change this gamma over 2 into alpha minus q. It's not hard to see that you should just get y divided by the length. The exponent is going to be 2 over gamma times alpha minus q. So this expression over here is this thing. And then we want to change the dc into dy. This is another thing like this. And now we simply exchange the role of the expected value in the integral against y. Because if you look at this quantity inside, it factorizes. This is the power of y times some power of the GMC. So you can just factorize the thing. Okay, so we've completed the computation. So let's translate this in English. Right, we've got this prefactor over here, which is some complicated thing, some moment of GMC. But the boundary length law is precisely going to be a power length law, where the exponent is 2 over gamma times alpha minus q minus 1. Okay, so it's a simple thing. It's got a complicated factor, but it's just a power law. And going back to what Ellen was saying, even though this correlation function is infinite or degenerate when alpha is less than q, you still get non-trivial behavior here when alpha is bigger than gamma over 2. I put a number out of nowhere, but this coefficient is non-zero, is between 0 and infinity when alpha is bigger than gamma over 2. So you still get non-trivial information. Okay.
So to do this change of variables, you need to know that the boundary length is finite under your measure,
I guess so, yeah, that's right.
which is not completely
Yeah. In this particular case, it's fine because we have this alpha, but it kind of goes away. So on the boundary, you're just looking at a free field, a Neumann free field with no modification. In other cases, you have to be more careful. Yeah, and then you maybe end up with this thing being infinity or 0 or something. Yeah, I'll say a bit more about that later when I talk about the Seiberg bounds. Okay.
Another question?
Yeah.
The expectation value, you say it's with respect to the free field.
Yeah, that's right.
And I wonder where does so the difference between the action function of the free field and of the Liouville field is this exponent times exponential. So where does that go in? Because you have the vertex operator, the alpha.
Yeah.
But where does the e to the gamma phi go?
Mm-hmm. Yeah, e to the gamma phi would be this boundary length. Oh, yeah, I guess we're setting this constant alpha to 0. So that one just disappears. Yeah, this was for simplicity.
So I think it is okay. You can do the same thing with not mu to 0.
You can do the same thing with mu not equal to 0, but you won't get a simple GMC measure. And the reason for that is this change of variables works when you have only one non-trivial observable. If you just have length, then you do this change of variables to get this. But if you have both length and area, you cannot do something like this. It doesn't simplify at all. Yeah.
Okay.
Yeah. Good. Okay, so I'm gonna check this line. Can people see above this line? Okay, no one's complaining, so we'll say yes. Okay, so the correlation function is the integral of negative this mu boundary times the quantum length. So we know the law of the quantum length now, so we're going to take that integral directly. And so it's just going to be, the same tree factor, and then we integrate e to the minus mu boundary y times, the power law. And this will directly give you the state and quantity up there. Yeah, I'm not going to write that last bit out, but you would just get that. And Okay, one thing I want to mention here is that this integral over here, this is an integral that defines your gamma function, and this is infinite whenever this quantity here is negative or non-positive. Did I say that right? Yeah. Yeah, and that's why we get this alpha bigger than q condition. Okay, are there any questions about this computation?
Sorry, I really need to, I think it's really stupid. What's the equality quantity with the exponential of alpha minus qc?
Yeah, so I guess that's, oh, this one, yeah.
This is the first equality.
Yeah, so this is baked into the definition, I guess you have your Liouville field, it's H plus C with, where you're stemming from Gaussian free field on the disk times e to the minus QC dc. And then for the field with an insertion of size alpha, this is basically e to the alpha phi naught times the Liouville field. And then this alpha phi naught, phi is a copy of C, so this gives you an alpha C, which will show up here.
And when do you see the H0? Ah, okay, so you're seeing the idea.
Yeah, so this is going to become e to the alpha H naught times something, and then you get an e to the alpha C times something. This one gets absorbed here. This one gives you a Jersanov shift to the free field. And that's why we have this log alpha log in the definition there. Yeah. Okay.
So so it doesn't come from this exponential minus new boundary L.
No. This stuff is just this is purely Gaussian. Yeah. Are there any other questions? Okay. So what I'm going to do now is erase this and write down the analogous result for the sphere case. And this will lead to the this Seiberg bounds that he mentioned on Wednesday. So we look at an endpoint function instead of one point. So you've got distinct points gi on the Riemann sphere C. Let's say we don't let any of them be infinity. And alpha I is a real number for each I. And what I'm writing down is basically the same thing. It's just a change of variables. Okay, so nothing fancy is going on here. We literally just take the definition of the Liouville field on the sphere, we do some kind of change of variables to get rid of the C, and then you end up with the same statement. So in general, your endpoint correlation functions of of Liouville theory are just going to be some kind of moments of the GMC measure when you add insertions to this, when you modify your field by some log singularities. This expression I wrote here is not 100% accurate. Maybe you have to add some kind of smooth function, or you have to normalize the field in with some choice of metric. But this is basically what you get.
And this is just the bulk, A is just the bulk Liouville
Yeah,
measure.
that's right, that's right. This is the bulk measure. So this is a sphere, so we just have the bulk measure. And unlike the boundary case, now you actually see the insertions. In the previous case, we looked at the boundary measure only, so we didn't see the insertions in the boundary GMC. But here we do see it. Okay, so this condition, alpha, sum of alphas is bigger than 2q. This corresponds to that gamma function integral we did. For that to be finite, you need this condition to hold. But there's one other way that this expression can become degenerate, and that's if this area over here is 0 or infinity or something. I guess it'll be infinity sometimes. So what happens is if any of its singularities is too big, if any of alpha I is bigger than q, then your field is going to be too big near the corresponding marked point. And what's going to happen is this GMC is going to be infinite. It's not even infinite in expectation, it's just infinite. And when that happens, of course, in this moment, here is going to be either infinity or 0. So things can be degenerate for either if this fails or if any of the insertions is bigger than q, bigger than or equal to q. And so that leads us to the Seiberg bounds. So let's go back to the slides.
So just to understand your study bounds, so so never when it is finite, the moments are finite, are infinite.
Never when.
So like you were saying that if you break the Steiner bound, then your mass gets infinity.
Yeah, or 0.
Infinity, and then my question is like, does it happen that you have finite mass almost surely, but your moments explode?
Yeah, that also happens. It's one of these stories where it's certainly possible for the GMC moment itself to become infinite. Let's see. Let me correct myself. So whenever your Seiberg bounds hold, you will never have this GMC moment being infinite. And that's because of this here. This exponent here is going to be negative. So, yeah. Okay, so I just did this slide on the board essentially. The point is your sphere correlation functions are non-degenerate if and only if you have these inequalities called the Seiberg bounds. So you have endpoints on the sphere with singularities of size alpha I at point zi. You need all your singularities to not be too big. And the total mass, the sum of your singularities has to be kind of big. So these are kind of pulling in different directions. And if you think about it, this means that you need at least 3 marked points. Right? If each of your marked points has size at most bounded above by q, and you want your total to be bigger than 2q, you need 3 points at least. So, so these are the Seiberg bounds, which arise in Liouville theory. This necessity for having 3 points also arises from the random surface perspective, because you need 3 points to fix an embedding of a random surface. I don't think I'll be able to speak about that today, but it's not just some artifact that comes from CFT. Okay, are there any questions? Yeah.
Do you have some intuition why the sum of the alpha A has to be bigger than 2q?
Yeah, so it's essentially because of this computation we did, where we have this, your field, yeah, it's essentially the analog of this thing over here. I'd be happy to chat more about it later. Yeah. Okay. Are there any other questions?
Maybe a comment about the 3 points.
Yes.
So if you want to find a metric of negative curvature on the sphere, you need to put at least 3 conical singularities. So this is the kind of analog that I think Antti was saying.
Right, yeah.
Maybe on demande some of the alpha cap bigger than 2 view. It's really to overcome the topological obstruction on this problem. If you want to find a metric with conical singularities, you have topological obstruction like the Gauss-Bonnet theorem.
Right.
And this sum of alpha cap greater than 2 view, it's really to overcome this Gauss-Bonnet obstruction. So.
Yeah, there's a lot of different perspectives about this bound. Yeah. Okay, so I just spent a lot more time talking about this first perspective of Liouville CFT. I want to discuss a second perspective. This is motivated by the perspective that LQG is a scaling limit of random planar maps. So we care about random planar maps, we care about interfaces, of statistical physics models, and we get these cutting and gluing type results. But because of that, we don't care what the embedding of the surface is. There are different ways to draw the same surface. So we want to mod out by conformal symmetries. So the object we care about is this quantum surface that we discussed yesterday briefly. We said a pair D, H is equivalent to different pair D tilde, H tilde if they have the same Liouville quantum gravity observables. So the area measures, these GMCs agree on the push forward, the boundary GMC measures agree on the push forward. Okay, so this is the notion of a quantum surface. It's not just a field, but you also have, you can mod out by conformal maps, basically. And the space of quantum surfaces is huge, but there's some very special ones. And we discussed the quantum sphere on Tuesday as being motivated by the scaling limit of a random planar map with the sphere topology. Okay, so I'm not going to go into detail here. I'm just going to say that this object is constructed in the continuum using the Gaussian free field. The exact definition is motivated by planar maps, but there are no planar maps show up in the definition. And it's an infinite measure. So for any fixed choice of area, the mass of spheres with an area is finite, but the total size of this measure is some power of A. You get this power law, as we've already seen in the other, analogous to what we've already seen. So QS with 3 areas is an infinite measure, because power laws always have infinite mass. Okay, so this quantum sphere was introduced by Sheffield, and this Liouville CFT stuff was probabilistic constructed by David Kupian and Rhodes and Vargas. And it's shown that these two perspectives are the same. And so what does that mean? Well, if we have a quantum sphere, we want to embed it inside, let's say, the Riemann sphere. But there's no canonical way to do this embedding. The easiest way to embed it is to sample 3 marked points and then do the embedding. So we consider the quantum sphere weighted by the cube of the area, and then you sample 3 points from the area measure. This makes sense combinatorially, right? Like if you have a random planar map calculated by a marked point, that induces a weighting on the total number of marked points, on the total number of points. So you have to weight by the area. This gives you a random surface with 3 points. A random surface is, a pair D, phi, modulo some choice of conformal map, and we choose the map that fixes the 3 points at 3, specified Z1, Z2, Z3 in the plane. So you can go from a random surface to a field phi by embedding it in the plane with your 3 marked points sent to Z1, Z2, Z3. Okay, so previous slide we have these ambiguous, this modulo embedding, and now we're fixing the embedding. And the claim is that when you sample this natural quantum surface called a quantum sphere with 3 marked points, and you embed it, the law of the field is precisely the Liouville field. So the objects that you care about that are motivated by random planar maps are exactly described by Liouville CFT. Okay. Are there any questions about this? A different way of phrasing this is that Liouville CFT can be nicely coupled with SLE. We'll see some examples of this. Okay. So the quantum sphere was motivated as the random surface that you should get when you take the scaling limits of spherical planar maps. You can do the same thing with the disk. Okay, and we can talk about this with particular boundary length L. So QD here stands for quantum disk. These are, and you can modify this object by adding marked points to it. You can weight by the total area and add a marked bulk point. You can weight by the total boundary length and add a boundary point, and so on and so forth. So, you know, this QD11 corresponds to the scaling limit of a random planar map with a disk topology with a distinguished bulk and a distinguished boundary point. And these are also known to be equivalent to the corresponding Liouville CFT objects. This first result by Baptiste shows that that the 3-point quantum disk is equivalent to the Liouville field with 3 marked boundary points of size gamma. And then we also have a similar result if we have 1 marked bulk point, 1 marked boundary point. Okay.
One question here, is it possible to have two bound points and one boundary point as well, or not? Two insertions in the interior and one at the boundary.
Yeah, you can do that sort of thing. But now what's going to happen is that, so the reason why these two in particular were stated is because these choices of 3 boundary or 1 bulk, 1 boundary, these are precisely what you need to fix the conformal structure. So what's going to happen if you have, you know, if you have 2 bulk points, for example, is you're going to get something like you have a quantum disk with 2 bulk points and 0 boundary points. And then you can embed it, let's say, into the unit disk. You send 1 bulk point to 0, and the other bulk point, let's say, goes to some point on this interval, maybe R. Then the field you should get is something like an integral. You have to integrate over the location of this point R. So if you have a dr term, then you should get a Liouville field with an insertion of size gamma at the origin, and another insertion of size gamma at the point R, and then maybe you've got some kind of density. Yeah. Okay, good. Are there any other questions? Okay.
Would you just click back one slide there?
Yeah.
Thanks.
Yes. Okay. So before we go to the break, I'm hoping that we can go through some explanation as to why we expect SLD and LPG should behave nicely together. So the story here is going to be again motivated under this. I have written up here a trivial bijection. On the left-hand side, you have the set of all planar maps with the disk topology together with a self-avoiding walk between 2 marked boundary points. Okay, so this walk is shown in red. Now, if I take a pair of scissors and I just cut along this red walk, that's going to give me a pair of planar maps, each having the disk topology and having distinguished boundary arcs of the same length, shown here in red. This is a bijection because if I start with 2 planar maps with distinguished boundary arcs of the same length, I can just glue them together along those arcs and I get this. Okay, so this is just a combinatorial observation. So let's imagine we can take a scaling limit of this picture. What should we get? On the right-hand side, we have a pair of planar maps with distinguished boundary arcs of the same length. These should converge to Liouville quantum gravity surfaces with boundary arcs of the same length. So that's what we get. And in this picture above, these 2 surfaces on the left and the right are independent once I specify the red length. Right. And so correspondingly, these 2 surfaces you get here should be independent given this red length L. So on the left-hand side, we have a self-avoiding walk on top of a planar map. It's not too much of a stretch to expect you should get Liouville quantum gravity with some kind of SLE curve on top of it. The part you cannot see in the discrete, though, is that they should be independent of each other. This is kind of a miracle. Okay.
Just one question, how you fix the size of the self-avoiding walk?
If you undertake a scaling limit, you need to weight by some Boltzmann thing. So you put maybe some mu to the length of the walk, and you weight by that. Yeah. You also have to weight the size of the planar map. So number of faces, there's some c to the n term you have to throw in. And so I've been deliberately kind of vague here, but yeah. This kind of scaling limit result is known to be true, and this has been proved by Ewan Gwynn and Jason Miller, or maybe, I guess that's in the full volume case. For the finite volume case, I think that's due to mean Holder and Simpson. But yeah, okay. Okay, the part I wanted to emphasize here is the continuous story you should get is a random surface with an independent random curve. And this independence, again, you kind of see it in the discrete. This independent pair, when you cut, gives you a pair of things which are conditionally independent given the lengths. Okay. Are there any questions about this? So this motivates a coupling theory between Liouville quantum gravity and SLE. It turns out that you need some kind of coupling between the parameters gamma and kappa. So gamma is a roughness parameter of LQG. The larger it is, the rougher surfaces. Kappa is a corresponding parameter for the SLE curve. And you always want to have gamma between 0 and 2, and kappa either gamma squared or 16 over gamma squared. So if it's gamma squared, you're going to get a simple curve because it's in the simple regime. If it's 16 over gamma squared, it's either self-hitting or it's space-filling. Okay, there's a quick note about this coupling. This is something that you can guess from CFT as well by looking at the central charges of your Liouville theory and your SLE curve. And you want these things to sum to 26. But okay, I don't go into detail there. So this theory was pioneered by Sheffield and then elaborated upon by Duplantier, Miller, and Sheffield, and they proved all kinds of really cool statements, such as if you take an LQG surface of infinite volume and you cut it by a suitable SLE curve, you get two independent surfaces. Or there's this making of trees result where you can glue together a bunch of continuum random trees, a pair of continuum random trees which are correlated with each other and somehow get a Liouville quantum gravity surface with an independent space-filling SLE on top of it. I don't want to go into detail about what these pictures exactly mean, but just know that there's a whole zoo of this kind of coupling results out there. And in all these cases, the curve and the surface are independent. Okay, you can kind of tell different stories by modifying the ones that we've already seen. And you can glue together surfaces which are disks to get a disk with a curve. You can glue together two disks along the whole boundary and get a sphere with a loop, etc. There are different topological configurations you can obtain. So I've been mostly, I should have mostly been talking about cutting, but you can also do gluing. And this gluing is what we call conformal welding. Yeah, maybe I don't go into detail about what conformal welding is, but there's a natural gluing operation for these random surfaces. Okay. So here's an example of a one such statement, which we can give, precisely if we know what quantum sphere and quantum disk are, which we do know because the quantum sphere is the random surface you get by taking this 3-point Liouville CFT, weighting by the cube area, inverse of the cube area, and forgetting the 3 points. And quantum disk can be defined from Liouville CFT. So you can view this as a statement that about surfaces that are described by Liouville. So the result is as follows. You take one of these quantum sphere surfaces, and on top of it, you draw an independent SLE loop. So SLE, I've introduced it as a caudal curve measure, but you can define a loop variant on the Riemann sphere. And this is a natural object. It satisfies some kind of conformal covariance, conformal invariance type statements. So you draw one of these quantum spheres and a loop on top of it, and you cut. And what kind of objects you get after you cut it turns out that you're going to get a pair of quantum disks which have the same boundary length L, and then you have to integrate over all possible choices of L. Okay, so a couple of remarks. The first is that this QDL is not a probability measure. It comes together with the partition function corresponding to the set of random surfaces with boundary length L. And then you further have this factor L in front of it, which corresponds to the number of ways to glue together your two surfaces, intuitively speaking. Like if you have a pair of discrete planar maps, each having boundary length L, and you want to glue them together, there are usually L different ways of doing this gluing, assuming that you don't have symmetries. So this kind of statement, you can guess that this kind of statement should hold from the heuristics that I've already stated, but this can also be rigorously proved. Okay. Are there any questions? Okay.
So is the C explicit or can it be computed?
That's an excellent question. So in many of these welding statements, you can compute the C, and the way that you would do so is you evaluate some kind of the size of some observable on both sides of the equation. In this particular case, it seems not so clear because this measure here is infinite. This SLE loop measure is an infinite measure. And so if you want to write down some kind of observable which is finite, it needs to take into account the loop somehow. I think we can compute this though, but it would be...
so one thing we need to specify is a precise definition.
Yeah.
That's like a measure.
Yeah.
You can only define up to a constant.
Right, exactly. Yeah. But I do think we do compute this quantity in our paper.
We computed in the specific case where the SI loop is chosen from CLE.
Yeah. You know, there are different definitions, but you can always, I think you can always make a computation if you can, if you know the SLE loop measure on, let's say you pass to a cylinder, and you look at the SLE loop measure restricted to the loops that separate the 2 points, you can ask what's the density of these loops in this dx direction. If you can, once you specify that, you can compute this kind of constant. Yeah. Okay. But that's a great question. These constants, you can often compute them, and they often won't be nice because they'll have some kind of Liouville CFT terms that show up. But yeah, it's okay. Then actually the constants should be pretty nice in general.
This one is pretty nice.
Yeah, I think we can discuss this further. Yeah. Are there any other questions? Okay. Yeah. So how much longer do I have? Do we take now, or do we have a few more minutes? Or?
You can, if you think it's a good time, you can have a bit longer for the second part.
Okay.
We started a bit late, so you can take also 5 to 10 minutes.
Okay. Okay, I'll just go for like 2-3 minutes, and then we can break. Yeah. So the last example of cutting that I want to state is as follows. So this is analogous to this picture I drew all the way back here, where you take a random planar map together with an Ising model, and you look at the plus boundary cluster, the cluster of plus spins touching the boundary, and you look at the holes that you get when you cut out. The objects that you get then are, inside the holes, are conditionally independent Ising decorated random planar maps, and they're only dependent on, all you need to know to sample them is how long are the boundaries. The same story holds in the continuum. So the analog of the Ising's model is going to be the CLE here. So if you take one of these, I should have drawn a picture in this slide, but actually, can we cut the projector altogether? I think this slide has too many words on it. Can we lose the slides, please?
The blackboard.
Yeah, blackboard. Yeah. Kind of guessing the year, something like this. On the left-hand side, you have one of these quantum disks, let's say with boundary length equal to 1. And you sample an independent CLE kappa on top of it. So the quantum disk is an LQG surface with parameter gamma. The CLE surface has its parameter kappa and they're coupled in the usual way. So kappa is either gamma squared or 16 over gamma squared. In this particular case, we'll just take gamma squared for simpler drawing. So you get these loops. So CLE is a random collection of loops which are either nested or non-nested, depending how you define them. We're using non-nested loops, so we're just looking at the outermost loops. And each of these countably many surfaces cut out by the CLE loops, these are going to be conditionally independent quantum disks. Okay, so this is kind of an elaboration of the earlier story I said, where you cut a sphere by a loop and you get two things which are independent. Now we cut the disk by this CLE collection, and once I tell you the loop lengths of all of the loops, the remaining quantum surfaces are conditionally independent quantum disks with these specified loop lengths. Okay. Are there any questions about this statement? This is done purely in the continuum by Miller, Sheffield, and Werner. Okay. Yeah, so let's stop here and we'll pick up after the break.